Title: The Architecture of Correctness. Today we will discuss an essential topic in algorithm design called the architecture of correctness. When we write a computer program, our goal is not simply to make it run. A program may execute successfully and still produce incorrect results. Therefore, correctness is much more important than simply compiling or executing code. Algorithm correctness is the process of mathematically proving that an algorithm always produces the expected output for every valid input. This idea is extremely important in software engineering because software controls banking systems, aircraft navigation, medical equipment, autonomous vehicles, and artificial intelligence. In such systems, even a single logical error can lead to serious consequences. Therefore, software engineers and computer scientists rely on formal methods to verify algorithms before deployment. Throughout this presentation, we will study the principles of algorithm correctness, understand how correctness is proved, and explore the formal techniques used to guarantee reliable software. Title: What is a correct algorithm? Let us first understand what we mean by a correct algorithm. Correctness is not defined by just one property. Instead, it is the combination of three essential guarantees. The first property is soundness. Soundness means that during execution, the algorithm never encounters unexpected behavior. It should not generate runtime errors, invalid memory access, undefined operations, or exceptions. Every instruction must execute exactly as intended. The second property is termination. An algorithm should always complete its execution after a finite number of steps. It should never continue forever in an infinite loop or endless recursion. The third property is validity. Even if the program executes successfully and terminates, it must still produce the correct answer. The output should satisfy the original problem specification for every valid input. Therefore, an algorithm is considered correct only if it is sound, terminates successfully, and always produces the expected result. Title: The Foundation, Preconditions and Postconditions. Before proving correctness, we first define a formal contract for the algorithm. This contract consists of two important components. The first component is the precondition. A precondition describes the assumptions that must be true before the algorithm begins execution. These assumptions define what inputs are considered valid. For example, if we are computing the square root of a number, the input must be greater than or equal to 0. Negative values violate the precondition. The second component is the postcondition. A postcondition specifies what must be true after the algorithm finishes executing. For example, after sorting an array, the postcondition states that all elements must appear in ascending order. Therefore, proving correctness means showing that whenever the precondition is satisfied, the algorithm always terminates and the postcondition becomes true. This idea forms the basis of formal software verification. Title: Proving iterative algorithms. Many algorithms use loops. Whenever loops are involved, proving correctness becomes more challenging because the same statements execute repeatedly. To solve this problem, computer scientists use a concept called the loop invariant. A loop invariant is a logical statement that remains true before and after every iteration of the loop. There are three steps involved in proving a loop invariant. First is initialization. Before entering the loop, we verify that the invariant already holds. Second is maintenance. We assume the invariant is true before one iteration and prove that it remains true after the iteration completes. Third is termination. When the loop finishes, The invariant together with the loop termination condition should imply the desired post condition. For example, during insertion sort, the loop invariant states that the first portion of the array is always sorted. Each iteration extends the sorted region while maintaining the invariant. Loop invariants are one of the most powerful tools for proving algorithm correctness. Title: Horde Logic, the Formal Language. Now let us introduce one of the most important concepts in formal verification, Horde logic. Horde logic was introduced by Sir Tony Hoare as a mathematical framework for proving program correctness. The basic notation is called the Hoare triple. It is written as precondition, followed by the program, followed by the postcondition. This notation means that if the precondition is true before execution, then after executing the program, the postcondition will also be true. Hoare logic also provides rules for reasoning about sequences of statements, conditional branches, and loops. Instead of verifying an entire program at once, we divide it into smaller logical components. Each component is verified independently. This systematic approach makes it possible to prove the correctness of very large software systems. Title: The Challenge of Loops and Recursion. Why are loops and recursion difficult to verify? Sequential programs are relatively simple because each statement executes exactly once in a predictable order. However, loops introduce repeated execution, and recursion repeatedly calls the same function. The number of iterations or recursive calls often depends on the input. As a result, manually checking every possible execution path becomes impossible. There is also the danger of infinite loops or recursive functions that never reach a base case. This is why testing alone is insufficient. Instead, we rely on mathematical reasoning using loop invariants and induction to guarantee correctness regardless of how many iterations occur. Formal verification provides confidence that the algorithm behaves correctly under every valid execution. Title: Why Formal Verification Matters. Formal verification plays an increasingly important role in modern computing. Traditional software testing checks only a limited number of test cases. However, testing can never examine every possible input. Formal verification provides mathematical proof that the algorithm works correctly for all valid inputs. This is especially important in safety-critical systems. For example, medical devices controlling patient treatment cannot tolerate logical errors. Aircraft autopilot systems must always behave predictably. Financial software handling millions of transactions must produce accurate results. Autonomous vehicles rely on correct algorithms to make life-critical decisions. Therefore, Formal verification builds trust in software by eliminating uncertainty and reducing the possibility of catastrophic failures. Title Summary: The Path to Guaranteed Correctness. Let us summarize the complete correctness verification process. The first step is writing precise specifications. These specifications define the preconditions and postconditions. Next, we choose the appropriate proof technique. Loop invariants are used for iterative algorithms. Mathematical induction is used for recursive algorithms. After that, we prove that the algorithm terminates successfully. Finally, we demonstrate that once execution finishes, the postcondition always holds. Together, these steps provide mathematical assurance that the algorithm behaves exactly as intended. Correctness is therefore not assumed, it is systematically constructed through careful logical reasoning. Title: Build with Confidence. As we conclude today's presentation, let us remember one important principle. Every computer program represents a promise to its users. That promise is fulfilled only when the algorithm has been proven to be correct. Formal verification transforms software development from trial and error into a disciplined engineering process supported by mathematics. Instead of hoping our code works, we gain confidence through logical proof. As future software engineers, data scientists, AI researchers, or cybersecurity professionals, mastering these techniques will help us build software that is reliable, secure, and trustworthy. In summary, correctness is not simply another software feature, it is the foundation upon which all dependable software systems are built.